In this video, I'm going to pick up and continue with the coding for the interrupt controller, the priority or programmable interrupt controller that's sitting here. Previously, I went through one video where I talked about the general theory behind this chip, and then later went into the actual connections, and I got all those connections done. And then got into actually, after that video, trying to get some assembly code working so that I could press a key and have that interrupt controller process the interrupt, get it to my processor, and then actually present something out on this LCD. And I was running into quite a few problems with that and could not get it to work. But at this point, if I press a key, it registers, I'm processing the interrupt. I'm not reading the key value yet or the scan code. I'm just simply processing and saying, okay, I acknowledge I've got the interrupt, and for now I'm just throwing out exclamation points out over there, regardless of which key I press. And you'll see that there's three that show up, and that's because every time I press a key, there's actually 3 interrupts that come through. And I'll address that later in some further assembly coding. But basically there's a down key and there's an up key. And on one of those, there's a double pulse that comes through. So I just got to do some filtering in the code to only recognize each key once. And that's a simple thing to do, or should be a simple thing to do. Let me just talk through what I've got here quick as a reminder. So on my schematic, I've got this interrupt controller, and I have done some updates through the schematic, and I posted the latest schematic. Feedback on a YouTube video real quick was that I wasn't necessarily showing my signals or my net names with some indicator showing that they were active low, like in this case. So I did go in and add in pound signs or hash signs at the end of everything that should be a low, active low. But previously went through and connected in from my PS2 keyboard this line here that will tell me every time I press a key, I'll see that flicker, but this signal coming over here is actually the opposite. It's an inverted, so it's on right now, it's pulling high, and when I press a key, it momentarily drops low when you see the LED momentarily come up. And then this here is just showing me which scan code, so that's great. That comes across over here then, and then from here, what you're seeing is I've got my bus connected to my data lines on that. I also have A1 connected here to A0. I'm bringing in that keyboard interrupt signal into IR1. And this, as you see it here, is correct. And so let me get over to the code for a minute and just talk through this. So if I go to this code, which I've also posted this code out on my GitHub, and I have a link from the blog page, part 2 of my building of this 286, there is links to the current code, and this is out there if you want to take a look at it, along with the Arduino monitoring and the Windows user interface that goes with that monitoring tool. I've posted all of that. If I get into this code, I'm going to kind of skip through any of the PPI stuff. I've previously walked through that code to control the PPI and the LCD, but let me get down here to where I get to the interrupt controller and just talk through what I have here. So if I go through this, what you're going to see first of all is that I had to set what addresses I'm going to use to basically manage the PIC. And I called it PIC M, that's PIC master, and P0 is for me just port 0, port 1. I see others call it control and data, or P1, P2, whatever. But these are my 2 ports that I'm going to connect to. And I have the PIC addressed at this 0010 hex. That is the I/O port that I have it decoded in my PSOC. And then I have the P1 decoded at 12. Now, to work with a PIC, I need to send it configuration data, and I need to send it what's called an ICW1, 2, maybe a 3, a 4, maybe, and potentially some of these OC 1, 2, and 3. And later what you're going to see is I'm going to write to these addresses whatever my configuration is. And I'm going to flip over to the data sheet for a minute. And this is the Intrasil version of the data sheet. If I go down into this document, they do explain what your choices are And I'm going to start with, this is a nice graphic. I had overlooked this at one point and initially was writing out IC1, 2, and then I was writing out ICW3, even though I shouldn't have been because I was not doing cascade mode. So someone caught that and suggested I ought to fix that, and I took care of that, so thank you for that. So now I'm going to call IC1, 2, I'm going to jump down and I'm going to write out IC4. And I need to understand, well, what do I need to write for each of these? And basically, I just need to put together a byte of data. And in this case, here's ICW1, and it says, here's your 8 bits. If it says A0 is 0, that means that that's that port 0 of mine. If it says A0 is 1, that's the port 1 that I've labeled previously. But if I get to ICW1, I need to send this according to that previous flow. I need to send this first. And when I look at it, this is telling me that, well, if I'm in 8085 mode, I need to set these. I'm not, so I'm going to set those as all zeros. I have to set this bit with a 1. What happens is the PIC is going to actually look for this A0 and this 1 in the D4 position and know that, oh, this is ICW1 that you're working with. And then I have to send it whether I'm going to do level or edge triggering. And I am doing edge triggering. So basically, when I press a key, what's essentially going to do is going to pull this high down to a low and then back up. And that rising of that edge is what actually tells the PIC that's an interrupt. So I am going to set my D3 of ICW1 to tell it that it is my edge triggered mode. And then I get into this ADI, and I believe for the x86 this really doesn't matter what you set it to, but I'm basically telling it that there will be 4 bytes that go with this call. Don't worry about the details. You can look at it further above. I don't think it's real relevant to what I'm doing. What is relevant for me is the fact that I am doing this edge triggering and that I'm doing a single controller, not a cascade mode, so I need a 1 for this single. And then I am going to tell it that I need this IC4, because later there's one value I'm going to specify in the IC4, which is that I'm using an 8086, not an 8085. And 286 would be the same as 8086 as far as this is concerned. So this helps me understand what are the different bits, and I can kind of put together that, or lay out that byte so that I can write it out. And what's going to happen is as I get down here into my code, I'm going to get down here to where I'm actually going to write that. What's going to happen is I'm going to assemble or put together that bit pattern. So I put in my code the comments that said, okay, I need to start out with a 0001. That's kind of just the way it is for this setup I'm using. That's always going to be the case. And then the next bit I can choose level or edge, and you can see I'm picking edge. And then am I going to do this 4 or 8? And I've got it at 8. I don't know if it even matters. Like I said, I think I read somewhere on the 86 that this really didn't matter a whole lot. But I could set that to a 02, I believe, a 0 also, and that would be fine. And then I have to understand, is it a single or a master that's going to go with a slave, or a slave that goes with the master is all part of this. And I'm saying I'm running a single PIC, so that is a 1. And I do need IC4 later, so I mark that as a 1. So that is my value. I think that's a 17. I then write that to that port 0, that P0. And then I've got to continue, and if I go back to my data sheet, I then need to move in and send in ICW2. So then I've got to understand what is ICW2 for. And now if I go up here, I think they do give explanations of each of these, so I can read up on what is ICW2. And this talks about what address basically is this first interrupt request going to be set to. And in my case, from the reading and the examples I was looking at, it seems like that is always set to 8 for my type of setup. So I am using 0x08 for this. And so that is setting the value, and then I'm going to go ahead and write that now to that other port. Like I said, sometimes called the data port, but P1 in my case. Then ICW3, I don't need, and that goes back to this where I just say, am I in cascade mode? And I'm not, so then that flips me over to ICW4. I've got this code in here, but it's commented out, so it's not actually going to do anything. Oh, and I had put in NOPs when I was doing some testing. These probably are not necessary. I'll take them out for now. I had just seen some commentary about wait states being required, and I'm going to go without the NOPs for now. I don't think those are needed right now. Then I get to ICW4, and I can go look at what do I need to send for ICW4. And if I look at ICW4, it looks like I'm going to send a 1000 no matter what. And then am I doing this specially fully nested mode? And I'm not even sure what that is. So I'm going to say, nope, I'm not using that. And then I have to pick, am I going to do a non-buffered or a buffered where I'm a slave or a buffered where I'm a master? And this is talking about things like data buffers, so transceivers and such. I'm not going to worry about that. I'm going to do a non-buffered, so that means I need a 0 here, and it doesn't matter what I put in D2, so I'll just do a 0, 0. And then there's this thing at the end of each of my procedures that get called when an interrupt happens that I have to basically set this EOI value to say I'm done. It looks like there's an option to have that automatically done for me. I'm not going to do that, so I'm going to go normal, so that's a 0. And then this last one, I'm going to say I am in 8086 mode. So really, I've got a 0, 0, 0, 0, 1. And if I go back and look at my code, that's what I am placing into this for the ICW4, is I'm just putting in a 1, and I write that out. At that point, the PIC should be up and running and ready to receive a request coming in. I then write out a 2 to my screen just to know I made it through all that. And then at this point, I actually enable interrupts. So the opposite of that, I disable interrupts early in my code. So if I step back up for a second, I come into my code here. Previously, it's set up just what these addresses are going to be for P0 and P1. I set up what's called this interrupt vector table offset. And it seems like for keyboards, that's like this position 9, and it's 4 bytes per. And I think this is just what it needs to be for my keyboard interrupt vector table offset is this 9 times 4, 36 decimal or 24 hex. You'll see the 24 later in the code. Or at least when debugging, I'll see the 24. Then I come in and I actually have the top of my code that starts up, which is right here. So when I reset the system, it goes to FFFF0. That tells it to jump to top. At the top, I then set up my registers. I disable interrupts. So I tell the processor, don't pay any attention to interrupts for now. I print some stuff to the LCD. I then get down to this interrupt vector table, and I basically have to write 2 bytes to this location, to that offset that was previously set, which was that hex 24 location. I have to tell it where is my byte, what's basically the address of where this KBD ISR is. So that is my interrupt service routine for the keyboard pressing a key. So if I scroll down, I have this KBD ISR. So it's going to grab relative to 0 to the beginning of this, what is the offset to get from the top of this down to KBD ISR. And I am going to take that location, which is 2 bytes, so a word, and I'm going to write that word of data to that offset, which is at the beginning of my RAM. I then move to the next location in RAM and write out an 8000. That is my segment. And so as I've come to learn with the Intel programming, very different from my 6502 world that I came from, I have to give it an offset. I have to give it, an offset here and then a segment here. And the way that that gets converted to a physical address is it basically multiplies the 8,000 times 16. In other words, it slides it left a character, if you want to think of it that way, and then adds on whatever this offset value is that it figures out from below. So that'll get me to a physical address of where basically this is going to sit. So where, and specifically where what's going to sit, where this procedure sits in physical memory. Where did I go? Right here, KBD ISR. So it's getting the physical address of that procedure and writing it into the very early part of my RAM. Because later, when an interrupt comes in, it's got to figure out, well, which interrupt is it? And then go look up where is it going to jump to so that it can jump to it. And it's going to do that lookup in the first part of my RAM to get to the right procedure address in my ROM, which is starting up at the physical address of 80000, working its way up. So that is how I am filling in this interrupt vector table for my keyboard interrupt handler. I think that is all correct, and if anybody is seeing something there that's not quite right, let me know. But I would say that it's working, because as I press a key, I do get that coming out okay. So then after that, I write out my ICW1, and so here's again the value for that. I put it into the lower A register, and then I write it to P0 of my pick. I then fill out what I want for values for ICW2, and I write it. I skip ICW3, ICW4, my values, and I write it. And then at that point, the pick is running. If I want, I can then also go in and use these other additional control words. And if I get into these, they are called operation command words. And there's different things I can do with those, and it talks about them here in the documentation. For example, I can mask out of all the interrupt request lines coming in, I can mask some of them so that they're ignored. Essentially, they're not actually processed. And then it goes through a similar thing where it talks about OCW1 and 2 and 3 and what do the different bits mean. And I, for now, don't need to do any of those. The OCW1, I did have some code in here previously so that I could change, what bits are masked out and then try to read it back. And so that's what I was doing. I was writing out these bits, and then later I was trying to read back the bits and see if I could write and read to registers in here, and that was all working fine. But I still wasn't getting my interrupts, which I'll come back to that here in a minute. So I've got that code commented out, and then I write a 2 to the screen. I then enable interrupts. I write out a 3 to the screen, and then I just sit and spin in this loop. Basically, that just stays right here. As I was troubleshooting this, I was getting all kinds of great ideas from those of you on YouTube and on my my website too. I appreciate all the feedback. So a lot of ideas were coming in, and I was doing quite a bit to actually test and see if I could figure out what's going on. And I have a blog post out there just on this troubleshooting stuff. So if you want to know more about that, you could jump out there. But what I was doing for testing, I did end up writing a little test here that basically just writes out a 1 to this register, this OCW1 register on the pick, and then it rotates the bit left and writes it and rotates it. And every time it rotates it, it clears my A lower and then reads it back. So basically I'm going to write it and I'm going to read it. And then I was looking at my logged output using my debugging tool to see, did it read back whatever it wrote? And that all checked out fine. So then I wrote an updated version of that actually takes a value, stores it in the lower D register just to remember it, writes it to the pick, clears it from the lower A, and then rereads it from the pick, and then compares what it read to what I temporarily stored in the D lower register. And if they don't match, then it jumps down and puts an F on my screen. And so I ran that at 4 megahertz effective clock speed for the processor, and it was running fine. I even had to manually just pull a wire while it was running, quickly pull it and put it back in, just to get an F to show up over here, just to validate the test was working. But at the end of the day, running a 4 megahertz processor, this was working just fine with no issues. By the way, at 8 megahertz, the system isn't quite running. It's close, I can tell, but I don't know. This is a 5 megahertz capable chip. Not everything I have here is even capable of 8, so we'll see if I can get back to 8 megahertz at some point. That's about it, though, for the code. And so if I'm sitting here in the main loop, I hit a key, that should then automatically jump down to my keyboard ISR. And what I'm doing in that keyboard ISR is just simply putting an exclamation point out to the LCD. And then I move back this value hex 20 into my lower A, and then I have to write that to this P0, that control port. And that is something that's just indicating I'm done with, and I don't understand the full reason why that has to be done, but I know it has to be done, that you have to write out this 20 to the EOI. So I'll spend some more time learning about that. And then I say return to whatever was running before this interrupt happened with this IRET. So that's about it for the code. And like I said, going back to this data sheet is very helpful. I did post on my blog post about troubleshooting some other links that were helpful, and I do have some of those at the top of the code too. So what I've been using as I've been going through this, besides the community and all the feedback and help I've gotten, is this book. This has been a good book by Mazidi and Mazidi. There's some sample interrupt code I found out there that was helpful. There's some sample code in that same book. There is a document where someone kind of gives a template of using the PIC, and that was helpful. There's the 286 hardware reference manual that's got a section on PICs and interrupts, and that was helpful. And then there's also this. This is an Intel document about using the programmable interrupt controller. So those I found all to be really helpful. Now, as I mentioned earlier, I was stuck at one point and got help from a lot of people, and some of the problems I was running into as I was going through this. The first one was I was calling or writing out, let me go back to the PDF here. I was writing out ICW 1, 2, 3, and 4, but I wasn't doing cascade mode, I was doing single mode. So sending ICW 3 was a problem. So that someone caught that really early. Thank you for that again. I took that out. Still didn't get my system up and running though. And I'll show you what the problem was. It ended up being something, the next problem at least, was a simple thing on my part that I had made a silly mistake. So here's my interrupt controller. So as I look at the interrupt controller, previously, when I laid out this schematic, I think if I remember right, I had moved this pin 17 down and I had moved pin 15 up so that I could just run this wire and not have to cross around a bunch of stuff. Problem is, as I've come back and referenced this, my brain was reading this as pin 15. So 1 through 14 on this side, wrap around to pin 15. So I was connecting my processor's interrupt to this last pin on the upper right. Well, that last pin on the upper right is actually pin 15, which is CAS2. So it ends up somewhat comically that this PIC has probably been working for a while, but I've been reading the wrong signal coming out of it. So I was going back through the data sheet and I saw, after staring at the data sheet 100 times, I came in here and I was looking at this and it's like, wait a second, why does that say CAS2 down here? That should be my int line. And I saw, no, wait, int is up here. And that's where I came back here and remembered I must have swapped those previously or moved those around. So my brain was looking at the kind of the location on the chip versus reading the pin number. So that was my bad. I picked up this connection right here from that last pin, slid it over 2, and now everything is working. So at the moment, I am running, I've got my clock halved, so I'm running 8 into here, and which means the processor's running at 4. If I reset this, you can see I've reset the screen back to the beginning. If I press a key, I get my 3 interrupts essentially per key. And if I keep pressing, it'll wrap around eventually. So there you can see it wrapping around on that LCD. But keys are being processed, and that seems to be working. So my next step then, being that the interrupt is working, now what I have to do is write code inside of here that when I get down to the keyboard ISR, I'm going to have to go then do a few things. But one of the key things I've got to do is run out to this PPI number 2, read the scan code, and then convert that to ASCII and print that ASCII character instead. I've also got to get in some code that filters out so I'm not putting a key in 3 times. And I think that should be similar to how it was done on my 6502, going back to Ben Eater's sample of how he did that and how he presented that in his video series. So that's next for me. Interrupt is being received now. It is jumping to my interrupt service routine. That is working. Now I just need code to read a value and get that to the screen, which I don't think will be terrible, but I'll work on that next.